Hi everyone, this is Mrs. GA, and today we're going to talk about the trigonometry of right triangles. So here's a quick reminder of your 6 trigonometric ratios. So given any right triangle and an angle theta, sine of theta is always going to be the length of the opposite side over the length of the hypotenuse. Cosine is the adjacent over hypotenuse. Tangent is opposite over adjacent. And then cosecant is the reciprocal function of sine. So notice instead of opposite over hypotenuse, it's hypotenuse over opposite. Secant is the reciprocal function of cosine, so it's hypotenuse over adjacent. And cotangent is the reciprocal function of tangent, so adjacent over opposite. So in example 1, we're told that the cosine of theta, some angle, is square root of 5 over 3. Find the other 5 trigonometric ratios. So whenever I have a problem like this, the first thing I'm going to do is draw a right triangle. You can draw it in whatever orientation you want, and you could pick either of these two angles to call theta. So let's say I call this theta. If we're told that the cosine of theta is root 5 over 3, that means the length of the adjacent side is root 5, and the length of the hypotenuse is 3. So before I start finding this 5 other trigonometric ratios, we're going to need to find that missing length, and we can do that with the Pythagorean theorem. So we could say 3 squared equals x squared plus root 5 squared. So x equals the square root of 3 squared minus root 5 squared. So x will equal 2. So now that we know the 3 lengths of the triangle, we can find all of our remaining trigonometric ratios. So we know that the sine of theta will be 2 over 3. I'm going to write cosine of theta again, but I'll write it in blue since we already knew it. And the tangent of theta is going to be 2 over root 5, which I'll rationalize to 2 root 5 over 5. Let me show that step actually. So 2 over root 5, which equals 2 root 5 over 5 if you rationalize. So remember, sine, the reciprocal function of sine is cosecant. So cosecant of theta is going to be 3 over 2. Secant is the reciprocal of cosine, so it'll be 3 over root 5, which is 3 root 5 over 5. And then the reciprocal of tangent is cotangent. So I'm going to take the reciprocal from here. The reciprocal of 2 over root 5 is root 5 over 2. And there's your remaining trigonometric functions. So remember, if you see something like this, draw a right triangle and fill out the legs you know, find the missing leg, and then the rest is just knowing your ratios. All right, go ahead and pause the video and see if you can give this problem a try. Okay, so here you can see that I set up the triangle, and I was able to determine that the opposite leg is root 7 and the adjacent leg is 3. Use Pythagorean theorem to find the length of the hypotenuse, and then the rest is just knowing your ratios. All right, so now we're going to do a quick review of what are called the special right triangle. So there are 2 triangles that you should know, like back of your hand. You should be able to memorize the ratio of the side lengths, and those are called 30, 60, 90 triangles and 45, 45, 90 triangles. So we know that for any 30, 60, 90 triangle, the relationship between the 3 sides always looks like this. Across from the 30-degree angle, we'll put 1. Across from the 90-degree angle, so the hypotenuse, will do 2. And across from the 60-degree angle is root 3. So this is always going to be the relationship between the 3 sides of a 30, 60, 90 triangle. So the hypotenuse is always going to be double the length of your shortest side. And the leg that's across from 60 is always going to be your shortest side times root 3. So if you can set up this special right triangle, You can find the lengths of any other 30, 60, 90 triangle using similar triangle ratios. But it's really important to know that when you're drawing your right triangle, across from 30 is 1, across from 90 is 2, and the last leg is root 3. Now in a 45, 45, 90 triangle, there's also a special relationship between the legs and the hypotenuse. So for these, I always mark it up 1, 1, root 2. So the two legs are always going to be the same, and the hypotenuse is always the length of the leg times square root of 2. So one really useful application of special right triangles is we can use it to evaluate trig functions of some of our unit circle angles. So we can actually use the special right triangles to find sine, cosine, tangent, cosecant, secant, and cotangent of pi over 6, which is 30 degrees, pi over 4, which is 45 degrees, and pi over 3, which is 60 degrees. So let's start by drawing a little special right triangle right here. So I'll call this 30, this 60, and then we mark it up. Remember, across from 30 is 1, hypotenuse is 2, and this is root 3. So for this row, we're going to use 30 degrees, and we're just going to use our trig ratios to fill this out. So if I do opposite over hypotenuse, it's 1/2, adjacent over hypotenuse, and then opposite over adjacent gives me 1 over root 3, which is root 3 over 3. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, so 2 root 3 over 3, and cotangent is the reciprocal of tangent, so we'll end up with root 3 after we rationalize. I'm going to skip 45 for now, and let's move on to pi over 3, which is 60 degrees. Again, just use your triangle and your trig ratios. So sine is opposite over hypotenuse, so root 3 over 2, then adjacent over hypotenuse, and then opposite over adjacent, root 3. And then we do our reciprocal functions, so 2 root 3 over 3, 2, and then root 3 over 3. So we can use our triangle to help us evaluate these expressions. Now for pi over 4, we're going to need to draw our 45, 45, 90 triangle. So remember, we marked that up with 1, 1, root 2. But it's the same process. Use the angle and then use your trig ratios. So if I do opposite over hypotenuse, it's root 2 over 2. Well, it's 1 over root 2, which we rationalize. Same for cosine. And for tangent, it's just 1 over 1, which is 1. So for cosecant, again, it's the reciprocal of this, or we know that it's hypotenuse over opposite, so root 2. Same for secant, root 2, and the reciprocal of 1 is 1. So a lot of people like to draw little special right triangles at the top of maybe their paper for their homework or maybe a test or quiz, and then anytime you're evaluating a one of your unit circle angles, so 30, 45, or 60 degrees, you can simply look at the triangle and reference it to evaluate. All right, so now we're going to be finding missing sides of these triangles, and notice that all of them are going to be special right triangles. So if you have a special right triangle or any really unit circle angle, I am going to expect that you can give me an exact answer without using a calculator. So when you see a problem like this, what you're going to want to do is you're going to want to create a similar triangle. So you're going to want to draw your own 30, 60, 90 triangle and try to match the general shape and orientation of this triangle so you can create ratios a little bit easier. So if this is 60, this is 30, and then we're going to mark it up with 1, 2, root 3. So since these are similar triangles, we can create ratios with their corresponding parts. So notice the two parts that we know for both triangles are this and this. So this is going to be kind of our baseline ratio. So I can say 7 root 2 over 2 should go with x over root 3. So I match up the parts. And then we just solve for x so we can cross multiply. So x equals 7 root 6 over 2. All right, we can do the same to solve for y. Again, start with your baseline matching sides. So the top one, it's 7 root 2, and that goes with 2 in your bottom triangle. And then y would correspond with 1. and that means that y equals 7 root 2 over 2. So by creating a similar triangle, all you need to do is to create the ratios of the corresponding sides. Okay, so here, notice that we have a 45, 45, 90. So we're going to draw our own, and again, try to match kind of the general shape and orientation. And remember, we do 1, 1, and then the hypotenuse is root 2. So the only sides that we know for both are the hypotenuse, so that's kind of our baseline ratio. So we can say 6 over root 2 should equal x, which corresponds with 1. So x equals 6 root 2 over 2, which is 3 root 2. And if x is 3 root 2, so is y, because this is, in addition to being a 45, 45, 90, it's also an isosceles triangle. So y also equals 3 root 2. Okay, and then for this last example, notice that we have two separate special right triangles. Here we have a 45, 45, 90, and here we have a 30, 60, 90. So I look at this and I say, wouldn't it be nice to know what the length of this leg is? So I'm going to call this one y. And to find y, I'm going to set up my own 45, 45, 90. Remember, the way we mark this up is 1, 1, root 2. So the matching parts would be 10 root 2 over 1 equals y over root 2. So if I cross multiply, I get y equals 10 times the square root of 4, which of course is 2, so y equals 20. However, we weren't trying to find y, we are trying to solve for x. So for here, we're going to set up a new special right triangle. So here's my corresponding triangle. And if this is 30, then I'm going to mark it up 1, 2, root 3. So we know that this length is 20, so it's going to be 20 over 1. That's the corresponding part, equals x, which corresponds with root 3, so over root 3. So if we cross multiply, we get x equals 20 root 3. So we had to use two separate special right triangles, and we had to kind of be strategic and say, hey, if I know this, I can find this, and that allows me to solve for x. Okay, so why don't you go ahead and pause the video and see if you can find the missing sides of these three problems. Okay, so let's check our work here. So again, make your similar triangle, set up your ratio, and cross multiply. So here you should get x equals 2 root 6. For part B, again, here's my matching triangle. Make sure it's marked up correctly. So 10 goes with root 3, x goes with 2, and y goes with 1. Those are the corresponding parts. Then for part C, I started by finding y, which is going to be the common leg that they both share, and I found that y is 5 root 2. So if y is 5 root 2, then I can use that to find x. So 5 root 2 goes with 1, and x goes with 2, and that would be my ratio. So you end up with x equals 10 root 2. Okay, so now we're going to talk about what it means to solve a right triangle. So if you're ever asked to solve a right triangle, it means to find all of the missing parts. So that might be all of the missing angles or sides or any combination of those. So here we know it's a right triangle, and we're given one angle and one side length. So to do this, I'm going to actually label this just to make it easier for me to describe what we're talking about. So I'm going to look at what we're given, and we're going to say, okay, I need to pick one of my trig functions to help me find a missing side. So let's say I want to find side B first. Remember, the side is always across from the angle. So B is the hypotenuse. So I know if I have opposite and hypotenuse, I'm going to use sine as my trig function. So I can say sine of 28 degrees, and again, we're solving for side B, lowercase b, equals 12 over b. And if I multiply both sides by b, I get this. And then I can actually divide both sides by the sine of 28 degrees. And then from here, you would plug this into your calculator to get a decimal approximation. And you should get approximately 25.6 if I round to the nearest tenth. I do want to point out that it's really important that you make sure your calculator is in degrees and not radians. So once I know this length, I can find the length of C by simply using the Pythagorean theorem. So we know that 12 squared, and remember we call this lowercase c because it's opposite angle C. So 12 squared plus c squared equals 25.6 squared, which is our hypotenuse. So c is going to be the square root of 25.6 squared minus 12 squared, which again you can plug into your calculator to get a decimal approximation. And here we should get approximately 22.6. And then, of course, to find our missing angle, we would just do our triangle sum theorem. We know that the three angles of a triangle should add up to 180. So 90 plus 28 plus 62 equals 180. So angle C equals 62 degrees. Okay, for the second example over here, notice that we are just given two sides, but we don't know either of these two angles. So one place we can start is by finding this side length, side A. So we can find that first with the Pythagorean theorem. So we can say 14 squared plus A squared equals 21 squared. So A is going to be the square root of 21 squared minus 14 squared. And you can get a decimal approximation of about 15.7. But now we have the issue of finding the angle. So we can either find angle A or angle B. Let's say we start with angle A. So look at the initial information we are given. If we're working with angle A right here, the two pieces of information I have are the adjacent side and the hypotenuse. So if you think about, okay, which trig function uses the adjacent side and the hypotenuse, we would use cosine. So we would say cosine of angle A equals 14 over 21. Now hopefully you remember, anytime we're trying to solve for the angle, we're going to use that inverse function. We're going to use arc cosine. So we can say angle A equals the arc cosine of 14 over 21. So again, anytime you're solving for the angle, we use the inverse function. So we use arc cosine, arc sine, or arc tangent. So this is something that you can plug into your calculator to get a decimal approximation for. And you should get approximately, let's see, angle A should be approximately 48.2. And then that's in degrees. And then we know that angle B will just be 90 degrees minus angle A, which is 48.2 degrees. So angle B is 41.8 degrees. And that's just that triangle sum theorem. So just remember, if you're trying to find a missing side length, like we were here, we just use the sine or cosine or tangent of the angle. If we're actually trying to find the angle, you need to use the inverse function. You need to use arc sine, arc cosine, or arc tangent. All right, go ahead and pause the video and see if you can finish solving these two right triangles. Find any missing sides or angles. Okay, so here I set up a ratio using cosine, and I wanted to start by finding C, our hypotenuse. So cosine of 40 degrees is 6 over C. adjacent over hypotenuse. So I got a decimal approximation for C, so approximately 7.8. Then you can find side A using the Pythagorean theorem, so it's approximately 5.0. And then angle B can be found using the triangle sum theorem. For part B, I started by finding side A using the Pythagorean theorem. And then I set up a ratio using cosine. So I said cosine of angle A is 20 over 25. And then if you're solving for the angle, you need to use the inverse function. So the arc cosine of 20 over 25 is approximately 36.9, which means the remaining angle B is 53.1 degrees. Okay, so now we're going to talk about some applications of right triangles, and that's going to be in the form of some word problems. So here we have a redwood tree casts a shadow that is 532 feet long. Find the height of the tree if the angle of elevation of the sun is 25.7 degrees. So angle of elevation and angle of depression are really common types of word problems for right triangles. So we'll talk about how to draw that. But let's start by trying to sketch a picture of what's going on. So we have, here's the ground, and here's our redwood tree. And we know that this redwood tree is making a shadow. There's the shadow. That is 532 feet long. So if the shadow is over here, that means that the sun is somewhere over here. So I'm going to draw the sun right here. So they would like us to find the height of the redwood tree. I'm going to call this X. If the angle of elevation of the sun is 25.7 degrees. So anytime you see the words angle of elevation or angle of depression, you need to always draw the angle from a horizontal line. So here we're just going to assume that the ground is horizontal, and then I'm going to draw my angle like this. So notice that it's from the tip of the shadow, it hits the top of the tree, because that's how shadows are made, and then it goes up to the sun. And this angle right here, the angle formed with a horizontal line, is 25.7 degrees. So it's really important whenever you're drawing an angle of elevation or depression that that angle is touching a horizontal line. Okay, so now let's look at the information we have and see how we're going to solve it. So I have this angle. I can assume that this is a right triangle. And I have an opposite and adjacent side, so I know that I'm going to use the tangent function to solve this. So we know that the tangent of 25.7 degrees is opposite over adjacent, so x over 532. So then we're going to multiply both sides by 532. So 532 times the tangent of 25.7 degrees. And then this is what you would plug into your calculator for a decimal approximation. We'll just round it to the nearest whole number, so 256 feet. So I think usually the trickiest part about these problems is drawing the picture. Just be really careful whenever you see the words angle of elevation or angle of depression. Okay, last problem together. So this one says a woman standing on a hill sees a flagpole that she knows is 60 feet tall. The angle of depression, so we're going to be very careful there, to the bottom of the flagpole is 14 degrees, and the angle of elevation right here to the top of the flagpole is 18 degrees. Find the horizontal distance from the woman to the flagpole. So let's see if we can draw a picture. So a woman is standing on top of a hill, and then she sees a flagpole. So here's the lady, and here's the flagpole. There we go. So it says that she knows that the flagpole is 60 feet tall. So we know from here to here is 60 feet. Now again, anytime you see the word angle of depression, you're going to need to start with a horizontal line. So I'm going to start by drawing a horizontal line from this lady going out and crossing through the flagpole. This horizontal line is just for us to have a reference point for our angle of depression. So it says the angle of depression from the lady to the bottom of the flagpole, so here to here, is 14 degrees. So this is the 14-degree angle. It needs to be touching your horizontal line. Then it says the angle of elevation to the top of the flagpole, so from the lady to the top, is 18 degrees. So that's this angle. Okay, again, since it's an angle of elevation, it needs to be touching a horizontal line. And they're asking us to find the horizontal distance, so they actually want us to solve for this. They want us to solve for x. And again, we can assume that this is a 90-degree angle, and of course, this is a 90-degree angle. So for this problem, you might see that we're given two angles, and we are trying to find a leg of a right triangle. But all we know is that the sum of these two legs is 60. We don't actually know what the individual ones are. So we're actually going to need to create a system of equations here. So even though we don't need to find this, I'm going to call this y. And if this is y, this means that this is 60 minus y, because the total is 60 and we call this y, so this is the remaining. So now that I have two variables, I can set up a system of two equations that will help me to solve for x. So let's look at this top right triangle. In my top right triangle, I have an angle, I have an opposite, and an adjacent. So I can say tangent of 18 degrees is y over x. And then in my bottom triangle, I can set up a second equation. I can say tangent of 14 degrees is 60 minus y over x. So from here, for my first equation, you can see that I can pretty quickly solve for y. Y equals x times the tangent of 18 degrees. So I can take this statement, and since I know that that's what y is equal to, I can plug it in right here. So we can say the tangent of 14 degrees equals 60 minus x times the tangent of 18 degrees all over x. So from here, I'm going to multiply both sides by x. Okay, so from here, you're going to notice that I have an x term on this side and an x term on this side. So I'm going to want to make sure that my two x terms are brought to the same side. So I'm going to move this to the other side of my equation using addition. And now that I have both of my terms with x on the same side, I can actually factor out the x. So I get x times the tangent of 14 degrees plus the tangent of 18 degrees equals 60. And then if I divide both sides by this entire thing, I have something that I can plug into my calculator to get a decimal approximation. Tangent of 14 plus the tangent of 18. Remember, tangent of 14 and tangent of 18 are just, they represent some decimal approximation. So if you plug all of this into your calculator, being very careful to group the terms in your denominator, you should get that x is approximately 104.5 feet. Okay, that is all for today's video. Thank you so much for watching.